So now we continue with the next speaker, Kirsten Haupt. We're really pleased to have you here, Kirsten Haupt from the
Thank you.
ITER Communications Office. And thank you so much for being here. And please, the floor is yours to tell us now all about ITER.
Well, first of all, can you see my screen and can you hear me?
I can hear you and we can see your screen. That's
Okay.
perfectly fine.
Yeah. So, yeah, I'm working at ITER. So, greetings from the south of France. I was invited to give you a virtual tour. So I will not go too much into detail into the science, but I'm going to go and continue directly from Ambrogio, and I'm going to whet your appetite because as I understand him and as I see at every conference we are going at the moment, workforce is a really important subject matter. So maybe by showing you some of the images of the ITER project directly now is going to help in that. So I will give you a very short presentation in the first half of my talk, and then I will take you on site with the interactive images that you can also access yourselves. And I leave you also at the end, I leave with Dario a 5-minute drone video that was published only 10 days ago. That's the very latest material we have. And I invite you all, to use it sometime during the conference, maybe as a further illustration. So for those, I understand also that not everybody is aware of ITER, that there are a lot of physicists and plasma physicists in your group, but also others who don't fall into that category. So just very, very quickly, ITER, and the background of ITER. ITER was basically thought of or conceived at the end of the Cold War in 1985, when Reagan and Gorbachev agreed to include the development of fusion as an aspect into their disarmament agreement when they met in Geneva. So a few decades later, we are here. You can see on the image, we are a project of more than 30 countries organized in 7 members, which is the European Union plus Japan, China, Korea, India, Russia, and the US. These countries cover about or represent about half of the global population and represent about 85% of the global GDP, which is quite powerful as support for the project. One important aspect I would like to mention, because I will be mentioning country names. Is everything okay? I hear voices. Is everything all right? Can you hear me?
Sorry, yes, we can hear you, Kirsten.
Yeah,
I don't know what the voice is.
I don't know. I had other people talking. Okay.
Okay.
All right. Anyway, sorry for that. One important aspect I would like to mention is that that ITER is an international organization and that the contributions to the project are primarily in kind. That means that all the countries that make up this project are actually producing the components themselves. That brings with it a number of benefits, as you can imagine, but also challenges when you talk about integration. If you consider that the giant components that we are putting together here to create this machine are coming from all corners of the world. So what are we doing? We are basing our technology on the magnetic confinement technology. That's what the tokamak is. You see the machine here as an overview. I will just quickly run you through the main components, and you will see also some video clips here. I heard a lot about the challenges connected with the development of fusion. You will see here some of the challenges just from the mere engineering of building the machine. So this is the vacuum vessel where, of course, the fusion reaction will take place. You have down below, I hope you can see my cursor here, a little person that gives you an idea of the scale. On the inside of the vacuum vessel, you have the size relations are 11 meters in height and 19 meters across. The parts, the vacuum vessel sectors are manufactured in Korea and Europe. And at the moment, we have 5 of the sectors here on site, 5 of 9. This is the first one that you see in our assembly hall. That is already a couple of years ago when that arrived. And that is the one from Korea. In the next video, that should actually start. Yeah, here it starts. You see the transition of that component into an assembly tool. You have a good glimpse into the assembly hall here at ITER. That's basically where everything is happening right now. And here this item is inserted into the assembly tool. So this gives you a good idea of the challenges we are facing, just the mere size of the components. What you see here, the vacuum vessel sector weighs 440 tons alone. Then magnetic confinement fusion. Of course, you need a good magnet system, a very strong magnet system. Again, I invite you to look at the figure down below. You get a good idea. We have here the main three parts of the magnet system. In the center, it's the central solenoid that consists of 6 colloidal field coils, all manufactured by the US in San Diego by General Atomics. That magnet will be one of the strongest magnets ever built when completed. We are now at the half mark. So about here, the first 3 modules have already been stacked onto each other. The fourth one is already on site. Then the next system is the toroidal field coils that you see here, the D-shaped magnets. There are 18 of those. 2 are always associated with the vacuum vessel sector. And the last big system here in the crosscut, the colloidal field coils, which are very large, ranging from about 9 meters to 24 meters here on the outside. So you can imagine, again, manufacturing was quite an issue, quite a challenge. So the four big magnets here, the 217 and the 224 meter coils were manufactured here on site by Europe. You see the smallest magnet as it's being inserted into the tokamak pit. That has been manufactured in China, but procured by Europe. That sounds a bit funny, but what we have done is also kind of outsourcing components if this was the better solution. Here you have the second magnet already inserted in the pit. That was the first one that was manufactured here on site, as it is with 17 meters, as it is too large to be put on the road and to be transported. And here you see, I hope you don't hear the sound.
No, we don't. We just
okay. I hear it, so I stopped it also. So that's I was actually there when that happened and took photos for this. That's a TF coil, and that was moved across the assembly hall into the let's do it again, into the assembly tool. Now, again, the challenges are in the engineering. Look at that. I mean, this coil is 360 tons heavy. That is basically a giant airplane. It's equivalent to a Boeing 747 fully loaded that was moved there at 360 tons. And we have 18 of those and 1 spare. All of those coils are already here at ITER. And then the third big component that I would like to show, and again, look at the scale. It's the cryostat, the big thermos that surrounds the entire machine. It's 30 meters high and 30 meters across. The parts were manufactured in India, brought here, and they were welded together into 4 subsections by a German company. You have here 4 sections. This is the base section, and you see its insertion in a moment, which is quite impressive. The lower cylinder, the upper cylinder, and then here the top lid. If you have a chance to come to ITER, which I hope you do at some point, you will see at the moment this top lid lying here on site and storage outside. It looks in a way, I always introduce it as our very own UFO because it really looks like that at its size 30 meters across. Here is the lowest section, the base section, which is basic, which looks a bit like a big soup plate, is being brought into the assembly hall. And here it is being inserted into the tokamak pit. This was a very challenging operation indeed. This component is the single heaviest component that we had to move at 30 meters across, 8 meters in height, and in weight, whopping 1,250 tons that were moved at an operational tolerance of 3 millimeters. So there are challenges everywhere. In the next video clip, I show you just in a few seconds the insertion of this item. So you see it here, how it is being lifted up from its assembly table where it was prepared for this operation. It's been moved across the assembly hall, and then it's inserted into the 30-meter deep pit where the tokamak where the machine is being built. So it was the first item that had to go in, and you see on the right bottom there the time, 24 hours. That's how long it took to bring this item into the tokamak pit. So lastly, a view into the tokamak pit. This is fairly recent. The video here as well, that is from our last drone video. So you will see that as well if you have a chance to see the drone video. If you don't manage doing your meeting today, I invite you to go on our website, which is a good point to find all sorts of resources on ITER on any questions. So here, you might have seen this already. I didn't see all of Ambrogio's talk, or might come up later. So this is how we imagine it looks like when it all starts working. So I come to an end now. We believe, of course, that fusion energy is our future. I have just come back from the climate summit in Baku, and the interest in the development of fusion energy is really indeed very big. So I can only repeat the call. Do decide to do something in fusion. We really need you. I'm going to stop sharing this one, and I'm going to go into the next, and that is, I hope you can see it. If someone could confirm it, Dario.
Yes, we can see. Yes.
Okay, now this is pretty cool. This is our 360-degree images. You can see here. I hope it's not too blurry for you, that you can actually manipulate it, and you see where we are, how we are situated here in the south of France. I am currently sitting in this building here. That's our office building for the ITER organization. And you see here the end of the crane. I'm in a room up here on the 5th floor. Normally I sit over here, and I can actually really see this whole setup quite nicely. So you see the whole site. This is of course now a little bit touristy, but why not to put some real images to the theory. This is where we are building the fusion machine in this building. This is the reactor building, the tokamak building. This is the building of the assembly hall that you have seen already before. And I heard Ambrogio mentioning tritium and tritium recycling. This is our tritium building. We have a full building for that to manage all the issues that we have to do in that relation. So let me guide you through some of the main parts of the setup. In front of you here in the two long buildings, these are the magnet power conversion buildings. They provide the power to the magnets. Let's go inside, and what you will see is giant bus bars. You can have a look around. You can do all this yourselves as well. It's all available on our website. So these are the bus bars that then go to the end of the building. So they're coming here, and then they're going up, and they're going over this end here into a bridge. And unfortunately, these pictures are already a year old. I'm working on the new set of 360 immersive pictures at the moment. Actually, I hope to be able to publish in a couple of days or 2 weeks about. So here you see the two bridges in construction. If you have a chance to see the drone video, you will actually see those bridges much further in the construction, and we actually filmed inside them. The next item that I would like to introduce to you is the cryo plant, which of course is manufacturing all the cryogenic fluids. So we have helium, we have nitrogen, mostly helium, which is very important, which will at 4 Kelvin cool the magnets, but it will also cool the thermal shields in its gaseous form at 80 Kelvin. All of that is done in this building. Incidentally, this building is actually the biggest cryo plant as a single installation in the world. Ours is in two parts. You have here the front part of the building, which is the compressor hall, coming up now. Yes, so you see that. It's fully finished. It's in the process of commissioning right now. The next building is where the helium is being cooled down to 4 Kelvin in these cryo boxes that you see here. And then through these cryo lines, it goes over into the bridges, into the cryo bridge. So that looks like that. So here you have the cryo plant, then you have here the cryo bridge. It goes across to the assembly hall, but then along the assembly hall, and it goes into this building, which is the diagnostics building, and inside it then continues into the tokamak building. And let's have an inside view. This is how it looks like on the inside, and this is now filled already with cryo lines, with the pipes. leading into the building. And in the drone video, you can see also the connection into the building. The PF coil building, I told you that some of the circular colloidal field coils were so big they had to be manufactured on site, just to show you where it is on site. So it's the longest building we have. And here you see the last coil. It is now in storage. It's 24 meters across. It is now in storage. Here you also have a view along the entire building. You see it's full of the different workstations. They're all dismantled by now. And this place is being used now for other activities, in particular repair activities of the thermal shields that had to be corrected. The pipes on them had to be corrected. So that is all being done in here. In the future, this building will be prepared to address other issues in the pre-assembly activities, namely on components like the diverter, the blanket modules, and the port plugs. Let me go to the heat rejection system. You, of course, know that ITER is a research project. We are not producing electricity. This is also not a prototype. That is what demo is going to be, where a power plant is going to be attached. We are evacuating the hot water. You see the complex cooling system down below, or as we say, heat rejection system. There are several setups. You have here the vertical pumps that sit on top of the hot basin, and they recirculate the water from here. All the water arrives in the hot basin, and from here it goes either back into the system through a set of heat exchangers that you see here. A lot of these components come from India. Or they go into the cooling tower and then they go back into the environment. We are using the water coming from the Canal de Provence, which is an irrigation system that was built about 150 years ago. We are using the water coming from there, and we are putting the water out again into the river Durance, but not without, of course, a thorough checking for any possible contaminants. We are going again into the assembly hall, which you see here, the double building, the tokamak building, and the assembly hall here. You see that it's fully reflective, which is really nice. Just a word on that, why that is covered in these reflective cladding elements. When the installation was built, there was a survey done in the local population. Today we call this social licensing, so including the local community in the development of an installation like that. And I have done that. And I've asked the local population here how they want this installation to look like. And the answers were, we would like it to blend into the landscape. I think that image shows that this has been quite successful, I think. Again, you have been already, virtually you've been already in the assembly hall. So here you see it again. It's one of our biggest buildings, 180 meters long, 60 meters high, 60 meters across. Center stage in this building are these assembly tools. We have two of those. This is where the vacuum vessel sectors are being equipped with thermal shielding and with toroidal field coils, which you can see here. I cannot see whether the thermal shields in this image are already on the vacuum vessel sector. I don't think so. It's not on there. What you also see in the back here is the beginnings of the central solenoid. In the video, this element is already a bit higher. You can also see the big overhead cranes that we are using to move our components, which of course are very heavy. I have given you some of the numbers. We have two giant cranes up top. Each of them have a lift capacity of 750 tons. And for the big components, they are used in a synchronized operation. Like when you look at this setup here, you have the vacuum vessel sector here in the center. Then you have a set of thermal shields around. You have two toroidal field coils around it. This whole module in the end will weigh close to 1,400 tons. So we need all the capacity the cranes can give us. Then a closer look into one of the assembly tools. We have given it a very long name. It's a subsector assembly tool. Again, we have two of those. And these assembly tools in themselves are first of a kind components, not our actual components for the machine, in many ways are first of a kind components, which poses specific challenges already, but also the tools that we are using for this are made for the first time ever. So also these assembly tools. So lastly, I would like to take you into the tokamak building. So you see here, the tokamak building and the assembly hall are connected in the top part. If I just go back, one more, wait a minute here. You see here in the back, you see a wall there. This wall is the separation with the tokamak building. This is actually already part of the tokamak building and runs as a nuclear building. You see that by the embedded plates here. These are steel plates that are embedded in the walls because it is not allowed under French legislation to penetrate these walls. Of course, for the sake of protection against radiation. That's, of course, fission legislation. That's another subject that's being heavily discussed at the moment to develop fusion legislation. But anyway, this is the wall towards the tokamak building. Let's go back there. And now I take you from the assembly hall, which is here, into the tokamak pit. And that's how it looks like at the moment. You see everything from above. I will take you down into the pit. Now what you can see here much better is are two sections of the cryostat. You see here the floor down below. And here, this is the base section that you earlier saw that looked a little bit like a spaceship. Then here, this part is the lower cylinder. And what's missing, of course, is the upper cylinder and then the lid, which are stored outside on the work site. Again, we have a special tool in here. It's not the central magnet. It has nothing to do with the central solenoid. That's a support tool. It will support the insertion of the vacuum vessel modules into the tokamak pit. And only when all of the modules are safely put inside will this tool be lifted out, and eventually the central solenoid will take its place. What you can also see down below is here the 17-meter coil, the first of the bigger coils that was inserted already. And let me show you in the bottom of the pit, you see these structures here. These are also magnets. They are smaller systems. These are correction coils because the magnetic field that is being created by the big system needs further correction. And that is done, the fine tuning is done by these coils. I actually have still another one that is the control building that you see here in the back. In the control building, you have the main control room that looks like that. There's not much to see yet. Even today, I was in there recently. It's still, it has a better flooring by now, but work is still ongoing. This will be the room from where the entire setup here is going to be run. There will be 80 operators sitting in there. And that again brings me back to my beginning and to what has been said already before, that we really need we need a lot of manpower in all sorts of areas, not just in the physics, not only in engineering, also in other subject matters. Look at me, I'm a communicator. We also need legal experts, administrators. So there are a lot. There's a big need, not only at ITER, I think in other projects as well. So I hope I have whetted your appetite a little bit. Again, visit us on our website. You find a lot of information there. Our latest drone video, I hope you can still see this today. And lastly, one of my jobs here is to run the visit program, and I also organize a lot of visits for students. If you ever manage to do so, please do come, let us know. You can register online, or you can contact us through the ITER communication email that is on our website. So I think I'll stop here. I don't see the time. Oh, I still have a little bit, so maybe there are some questions.
There are some questions, Kirsten. So thank you very much for the nice presentation. We will make sure that the drone video is broadcasted today. We will see where we fit it, but of course, I think it was really interesting. Thanks for the nice presentation. It's outstanding how ITER looks like, and also all the visual resources that you have to show to everybody how it looks like. So let's go straight into the questions because we have some of them. I think the first one you already answered. That is, if it's possible to do an in-person tour of the ITER site. You said yes.
Absolutely. Yes, absolutely.
Go through the website and then you will contact Kirsten and the team. Then the second question is, when is the ITER project expected to be completed?
That's a good question. At the moment, we have already heard that there's a new baseline that has been discussed, and I think it's been probably agreed these days. I cannot actually say that. We hear the results today, because actually yesterday and today we had the ITER Council meeting here at ITER. So the proposal that was made in May with the new baseline, we expect it to be approved, and then that's our new marching orders. And we will have, in a very simple way, an overall delay for start of operations of 4 years. So the idea is to start in 2039. So that is when the machine is completely finished as a machine, and experiments will start. And that will last quite some time. I mean, probably 2 decades, if not even more. Before that, though, just one word on the difference between the previous and the current baseline. Previously, we had a staged approach where all the steps towards the finalization of the ITER machine were sort of consecutive. Because of the delays we have experienced, that was completely changed, and the progress was done in parallel. As long as repairs were going on, we were able to move ahead on other issues, and that helped us to reduce the length of the delay a little bit. So it is now 4 years in 2039, if agreed today by the ITER Council. So you will see that on our website later today or tomorrow.
Okay, thank you. That's good to know. Then another question is the bus bars. I think that means the coils. Are the coils superconducting or copper?
There is copper in there, but they are superconducting. On the exact technology, I cannot really tell you, but the coils are superconducting. They are, the bus bars have nothing to do with that. The bus bars are just the industrial level power cords for the magnets, but the magnets themselves are superconducting. All 3 big systems that I showed you, so the central solenoid, the toroidal field coils, as well as the poloidal field coils, as well as the correction coils that I showed you, there will be X-vessel correction coils. They are also superconducting, meaning they are being cooled down to 4 Kelvin by liquid helium. Right, and the material inside is a niobium titanium or niobium tin with a bit of copper. We have other correction coils that are in vessel correction coils, and those are actively water cooled. They are not superconducting.
Okay, thanks. And there is a question if you could recommend some reference about cryogenics, and also if ITER accepts some interest from Brazil.
Oh, that's very interesting. I thought there were discussions with Brazil already. I don't want to jump the gun. I know that ITER is in talks with lots of countries. Due to the organization of ITER, we are based on an international agreement. We cannot take on new members. That's legally basically not possible. But what we do is we have a lot of cooperation agreements. And we have them, for instance, with Australia, with Kazakhstan, with Canada, and with Thailand. And I really don't want to say anything wrong, but I thought there was something in the making with Brazil as well. But I mean, please don't take my word for it. I don't know exactly. I didn't understand the question on the cryogenics.
No, it's maybe we could recommend some references, but I think
in
just
what
go
way references?
In literature, I'd say, but just go to the ITER site, I guess. And
yes, go to the ITER site. We have a section on there in particular that's concentrated on education, and it's called Infused. So if you go to the carpet section of the ITER website, you find a section there, education. When you open that, you see one category there, Infused. So that's where you find more material. And then, of course, you can also browse our website. Some of our articles are quite technical. There is a whole range of levels in there. I mean, there's some high-level general articles, but there are also quite a number of technical articles. So if you look for cryogenics, maybe you'll find also more connections there.
Okay, thank you. I think I'm going to take the last question because now we're in the coffee break. But before I do that, there is a nice comment from Mohammed saying this is the equivalent of pyramid. It's fascinating. I think I agree with him. But then the last question would be, is beryllium still a candidate material for the primary wall, or is tungsten the final choice?
I think tungsten is the final choice. That has already been made, that decision. You see, the initial idea was to use beryllium during the construction phase and the initial test phase, but then the idea was anyway to replace the first generation, first of all, of beryllium with tungsten. Now that step has been just shortened. We are going straight to tungsten.
Okay, thank you. Maybe one last question, and then we close it because you were so fast. So just maybe it's an interesting one. Is where the risk due to climate change, like wildfires, floods, heat waves, consider when choosing the location of the ITER project?
I've never heard that question, but it's quite interesting, in particular with the wildfires. But I think we are quite protected here. We have actually our own fire engines on site, so I think there is enough protection there. The reason, just to go to that, I mean, the reason why we are here has to do with the expertise, with the nuclear expertise of our neighbors. So there were several candidates, and several conditions were posed to choose a site. All of them had to have nuclear expertise nearby to start building the core of the setup. And we have here the French Atomic Energy Commission as our neighbor, so that was a given. And another very important condition was the logistics, to be close to a big harbor, because most of our components that come from the member states, if they are small enough to be shipped, they have to come here to a port, and that the port is near here and close to Marseille, and we have a 105 itinerary to our place here. So that was a reason. You have risks everywhere, I think. Yes, the specific risks here in this area here is the heat. Sometimes we have heat waves up to 45 degrees. There are forest fires, but here near us, I have not heard of any. I'm here now since 7 years. Where I live, there is more of a risk, that's in the hills. But here there are so many installations. We have CA next door. So I think the French authorities really monitor this very well. Inundations, we don't have that here either. There is no risk here. It's in other places around, but not here. We are actually a little bit on a hill, so to speak. So we don't have that. We don't have that issue. But the heat, I mean, the general temperature is going up quite a bit, but maybe one last word on that. In the assembly hall that you see, we have a very strong HVAC system, right? So that is running the whole year. And that brings the temperature to 22 degrees, about 22, 23 degrees all year round, winter, summer, no matter when. So that takes care of the impact of potential heat waves or cold temperatures there. But that has to do with the engineering and with what you can imagine, metal expansion, if you have such a range of temperatures. So that's taken care of by that.
Okay, Kirsten, thank you very much. Yes, thank you very much for answering all these questions, for the presentation. Thank you. Great having you here.
And I hope you have find time to see the video. It's really nice.
We will make sure, yes.
And keep an eye on the website. I'll be publishing the new 360-degree tour in the coming, well, let's say in the coming weeks. And to those of you who are into sort of virtual reality goggles and stuff like that, you can connect those as well. So it's not just in 2D, you can also really see it in proper 3D. All right.
All right. Thank you very much, Kirsten.
Have a nice meeting. Ciao.
Thank you.